G'day everybody, my name is Reese and this is my short video series where I show you how to do cool things in SPSS in less than 10 minutes. In this video, we'll perform an analysis of covariance in SPSS. A lot of the output and interpretation of an ANCOVA model is similar to that of a normal ANOVA. Therefore, for the purposes of this video, I'll be highlighting the components which are different about performing an analysis of covariance. The key difference here is that there is an additional assumption in ANCOVA called the assumption of homogeneity of regression slopes. This video will highlight the importance of testing this assumption in SPSS.
Alright guys,
and how to actually
formally
formally do so.
So we're now ready to start exploring our first analysis of covariance. Now if you've already watched my simple linear regression video, you would notice this data set is the same. So in this particular data set, what I have here is the analysis or the exploration of how different program types of teaching, so I've got 3 different levels of teaching: supervised study, didactic, and problem-based, how that impacts test performance. So the hypothesis being here, or the research question, does type of program or teaching strategy impact test performance? It's fake data. I've simulated it just for the purposes of this video series, and I've also got another variable in the mix here, IQ. So what I explored in my simple linear regression video was, how does IQ relate to test performance? Now what we're going to be doing in our analysis of covariance is looking at how test performance differs across different teaching strategies after controlling for IQ. Because the real hypothesis here is there a difference in test performance across different teaching strategies? Now, of course, people's performance is going to be strongly related to their IQ level. So what the purpose of an ANCOVA analysis is, it's all about comparison of means, just like a one-way ANOVA or a two-way ANOVA or any analysis of variance design. But it introduces a controlling mechanism into the analysis. So we're able to compare means across an IV like program type on test performance after controlling for IQ. Now that's like an extremely powerful technique to have, because whatever conclusions we make about mean differences in test performance across program type, if we control for IQ, we know that those differences in performance wouldn't have occurred from IQ levels alone. So it's a controlling mechanism. So you may have read research studies that say such and such found a relationship between this and that after controlling for age, gender, ethnicity, all these like demographic-y type variables. It's the same sort of concept. So an ANCOVA is a first stage analysis, or a first analysis type that students often get introduced to, where you can control for variables. So IQ in this instance here is called a covariate. What I'm going to do first of all though, I'm going to run this as a one-way ANOVA, just for a little bit of revision for you. So I'm going to go to Analyze, General Linear Model, and then Univariate. And I'm going to test to see whether there's a difference across programs. So I've got program type as my fixed factor, and I have test performance as my DV. And I'll keep all the options set to default for the time being. I'm going to go ahead and click OK. And here is my ANOVA table here. If we scroll our eyes across this row here called program type, you'll see that the F ratio is quite small, and the result here is statistically non-significant. So if we were to perform a one-way analysis of variance, comparing mean differences across program type on test performance, we would conclude that there was a non-significant relationship present based on this p-value here. Now, this is a one-way ANOVA, this isn't an ANCOVA yet, so what we're going to now do is we're going to go back into that analysis, and this time we're going to make things a little bit more complicated. We're going to drag IQ down to be a covariate. So the covariate is going to slot down into the covariate box here, and we're going to hit OK. And what you're going to see here is we get a new ANOVA box here with IQ in the equation and also program. And what this does is it allows us to have both of these variables in the model simultaneously. So we can now see that program type does in fact have a significant relationship on test performance after controlling for IQ. So how that manifests itself is you can get these occurrences where a result is non-significant when you look at an IV by itself, simply due to the mathematical calculation of an F ratio. So an F ratio is the between groups variance divided by the within groups variance. Now, if you have a really large error term, so if you have a lot of unexplained variance in your model, what that can do is it can make your F ratio really small, therefore your result is non-significant. Whereas, remember this little error term here, remember these numbers here, if you compare them to these error terms here, this one here, 1638 being the main one, the sums of squares error term here, it's much, much, much smaller when we've introduced IQ in the model. So what that does is it becomes a more sensitive test measure here via controlling for IQ. So you often hear that an ANCOVA is more sensitive than a one-way analysis of variance because you do reduce that error term by including good covariates into the model. Key note there being good covariates. You don't want to just enter in random rubbish. You want theoretically driven variables as covariates that you feel would control for a certain amount of variance and allow a more sensitive or a more accurate picture of your key IV here. So if we were just to wrap up the analysis here, we'd be able to conclude that there was a significant effect of program. Now, me showing you this ANCOVA model here is actually jumping the gun a little bit. But the reason I wanted to do that is I wanted to demonstrate to you what the hell ANCOVA is, first of all. So I wanted you to see that a result can actually be non-significant as an analysis of variance, but then when you include a covariate, it actually becomes significant in certain circumstances. So you can really see the purpose and the design of what an ANCOVA model is designed to do. Now, the reason I said I jumped the gun a little bit is because before you perform any statistical analysis, you should always look at your assumptions. And that's no different for analysis of covariance. In fact, analysis of covariance has all the same assumptions as a one-way or a two-way ANOVA, but with the addition of some special ones as well. And I'd like to highlight one special assumption for you today in this video. It's called the assumption of homogeneity of regression slopes. And what it states is, it states that whatever effect your covariate is having, whether it be positive, negative, whatever it may be, that effect must be the same at each level of your independent variable. So what we essentially want to see is we want to see no interaction effect between IQ and program type on test performance. Now, the bad news is that SPSS doesn't give us a button or an easy way to actually do this. So what we've actually got to do is we've got to fit a special custom model to explore this assumption. Now, again, if you were running your own analysis of covariance, you'd actually do this stage first. So if you're just analyzing your data, go straight to this assumption first and then run your official ANCOVA, similar to what I've done before. So I'm going to go ahead here and fit a custom model. So I'm going to go and hit Model, Custom, and then it lists your variables on the left-hand side. I'm going to drag Program, IQ, and then both of them across as an interaction term, and then hit Continue. I know it's very odd, but unfortunately there's no other way of doing this. And then hit OK. And what this allows us to do, we get this additional row here in our ANOVA table, which is program by IQ, so that little star means multipliers. This is the interaction term here. And what you want to see here is a non-significant interaction term in your model. If you see an interaction term, I strongly suggest you consult a more advanced statistical textbook. We do not have time to cover how to get around this assumption in this video, because this is quite a severe violation in an assumption, and unfortunately you cannot progress in an analysis of covariance in a normal way when this occurs. Good news is that it's quite rare, but I should flag it as a concern for you. You should always check this assumption first before running your ANCOVA. But because our result here is non-significant, we've got absolutely nothing to worry about. So we can actually go back into I'll go the slow way, analyze general linear model univariate. I won't take any shortcuts for you. And what we could do is here, we can reset this analysis to get rid of that custom model and just start again. So type of program is the fixed factor, test performance is my DV, and IQ is going to be my covariate. And just like with a normal between subjects ANCOVA, you can ask for contrast, you can ask for plots, you can ask for different options. So maybe I want to do some follow-up tests on the different types of programs. I could certainly do that. So I could compare the main effect for program. I'm going to Bonferroni adjust my confidence intervals there. If you don't know what I'm doing there, I suggest you revise type 1 and type 2 errors to understand what a Bonferroni adjustment is. Just like in normal ANCOVA, you can ask for other things like descriptive statistics, effect size, homogeneity tests. So there's still an assumption of Levene's you've got to look out for. So still look out for that. You could ask for your eta squared figures, lots of things that you could ask for. I'll keep things nice and simple though. I'll just ask for, let's collect descriptive statistics. Let's just chuck on effect size. Oh, what the hell, let's do Levene's too. We'll go ahead and hit continue and then hit OK. And what we've now got, it's telling me what my variables are. It's giving me a table of descriptive statistics, so my means and the standard deviations. So I can see here that the means are progressively going up. So supervised study had the lowest test performance, then didactic, and then problem-based. Good news is that Levene's test of homogeneity of variance is not significant, so we haven't violated that assumption. And now this is my official ANCOVA model, so note how there's no interaction term. That means I'm actually testing the ANCOVA model. If you see an interaction there, that means you're testing the assumption of homogeneity of regression slopes, not the official ANCOVA model that you would use for your written report or a write-up. So here we can see program is in fact having a significant effect on test performance. IQ is also having a significant effect on test performance, but oftentimes when you include a covariate into the model, you don't really care about what effect it has because it's only there as a control mechanism. It's only there to be there or there to make the effect of your key IV program type more pronounced or more accurate. So you definitely still report it, but it's not really something that you're going to jump up and down with if you get significant results, because oftentimes it's a bit of a no-brainer because IQ scores would have been introduced into this model because it had such a strong correlation with test performance, and you wanted to see program type more clearly after controlling for it. I've also got an additional column there with my partial eta squareds, which could be used in the reporting process of an ANCOVA model. And if I scroll down here, I just chose to do some pairwise comparisons. If you were running this analysis for yourself, you'd have to check your hypotheses about whether it was more appropriate to do plan contrasts or follow-up post-hoc pairwise comparisons, whatever the particular research scenario lends itself to. I just wanted to show you something very, very quickly, because the pairwise comparisons do something quite tricky here. So if you were to compare the means and the means here for the follow-up test, so supervised study 70.253, that's actually different from the initial mean that was reported before, 70.22. It's very close, but it's a little bit different. It's the same thing for didactic, 75.68, 75.56 up above. So you can see some small differences depending on where you report your means. However, these means here are what's actually being looked at in your pairwise comparisons. And the reason that they're a little bit different is because the second table of means here have been adjusted for based on your covariate. So what's actually happened here is the means have been recalculated based on the IQ levels being introduced into the model. That's very different from the means up here, which were not adjusted for by the covariate. So these first descriptive means are not controlled for. The second lot of means have been controlled for, and it's these controlled means that find themselves into the pairwise comparisons for follow-up tests. And in which case here we can see that there was a difference between all of the conditions. There was only one non-significant result, and that was between didactic and problem-based programs, or problem-based and didactic teaching strategies. And that's essentially it for running an ANCOVA model. Once you understand the whole idea of why we do an ANCOVA in terms of controlling for a covariate, and understand how to test for the assumption of homogeneity of regression slopes, the reporting of F ratios, the interpretations of effect sizes, your choice of follow-up tests being dependent on your research hypotheses, all those sorts of things, they remain the same in an ANCOVA model compared to just your normal run-of-the-mill analysis of variance. Alright guys, that wraps up our short video today on analysis of covariance. I hope this short video has given you the ability of running your own ANCOVA models in SPSS, and you're able to see how a lot of the output is consistent with that of a normal, simple one-way ANCOVA design. The key difference highlighted in this video is the assumption of homogeneity of regression slopes, which is unique to an ANCOVA model. If you need help with reporting an ANCOVA model, I strongly suggest you consult with your prescribed text. Cheers guys, I'll catch you for my next video.